So if you are graphing y equal to 4 minus 2 sine of x, you can totally rewrite that as -2 sine of x plus 4. So then the negative here gives us a vertical flip. The 2 gives us an amplitude of 2. And the plus 4 shifts it up 4. So that's how we graph something like that. So this would, so I would shift it up 4. So my new middle line would be y equals 4. And then my amplitude's 2, so I'm going to go 2 above and 2 below. So I'm going to go as high as 6, as low as 2. And then usually sine would start, well, sine would start in the middle. I guess I need to draw my period. My period hasn't changed at all. My period is just 2 pi. Cut it in half. So whatever your period is, you're always cutting it into 4 equal quarters. Never a different number. You're not dividing by 6 or by 2 or by 3. You're always dividing by 4. So my period divided by 4, 2 pi divided by 4 is pi over 2. So I'm getting 0, and then pi over 2, and then add pi over 2 to get pi, and then add pi over 2 to get 3 pi over 2. So usually sine would go middle, top, middle, bottom, middle. But since it's flipped over, it's going to go middle, bottom, middle, top, middle. So the sine function would look like this. That's how you graph something like that. But the real kind of the trick here is to recognize that it's just written in an atypical way. Yeah. So tomorrow I will spend more time talking about graphing sine and cosine and kind of the process of taking the period, dividing it into 4 equal subsections, and then kind of finding these 1, 2, 3, 4, 5 points by taking your first point and then adding a quarter of the period. In fact, let me just spell it out right. This length here is 1/4 of your period. This length here is 1/4 of your period. Right? Whenever you're graphing sine or cosine, these places that are 1/4 of a period away from each other are the places where you get the middles, the lows, the middles, the highs. It's where you get your 5 kind of key points for graphing sine or cosine. It's just they're spaced out differently depending on how long your period is. But it's always 1/4 of whatever your period is. Okay, so sorry, I was saying something else though. I was saying that next week, sorry, let me look at the schedule just to be absolutely sure. The calendar says next week we have, I think the calendar says next week we have class Z, but yeah. So next week, Trig, so Monday, Trig review. We're not going to talk about limits. We could, I mean, if you guys really want me to, we could talk about limits, but I certainly have the impression that our time would be better spent talking more about trigonometry, specifically like angles that are multiple revolutions around and finding the reference angle and finding sine or cosine or tangent of those angles. So I think I'm going to decide if there are things you think are important to review, you're certainly welcome to send me a message, send me an email, say, hey, James, I'd like to see more of this next week before our final. But my plan next week is to kind of just spend a bunch of time reviewing trigonometry, graphing trig functions, evaluating trig functions, talking about reference angles, all kind of like the key things that you will need to be able to do next quarter when you're taking either the 16 or the 17 series. I believe if you're planning on taking the 21 series, I think there's another kind of class to take before you take the 21 series. So yeah. But so I guess if you're planning on taking the 21 series, send me an email and we can talk about what the plan should be for your next quarter. All right, let's go ahead and talk about graphing some things. So yeah, we're going to talk about graphing tangent and cotangent and secant and cosecant because they are graphs that you will see next quarter. And I would really love for this. Let me ask you guys, how bad is the glare right there? Is it terrible? When I write stuff on the board right here, is it really hard to see?
I don't think it's that bad.
Okay.
Usually if you have like a dark
All
marker.
right. To me, it looks really bad, but maybe it's just because my monitor is showing it that way. Okay, good to know. I just see it all the time. I'm like, oh, I'm like, I can, when I'm looking at my screen, I feel like it looks really hard to see whatever's written right here. If you guys say it's fine, great, good to know. All right, so let us get, I guess I won't worry about trying to move things around then. Let's go ahead and graph tangent, cotangent, secant, and cosecant. And again, we'll kind of start off graphing these things by plotting a few points, and then I'll talk about how you really graph them. So let's talk about tangent first. So I want to graph y equal to tangent of x, or if you prefer, f of x equal to tangent of x. And so it's kind of important to know about the values of tangent. So let's make a little table. And on this table, we're going to pick our x values and our y values. And the x values are going to be the usual nice angles that we pick to evaluate your functions at. So like 0 and pi over 6, and pi over 4, and pi over 3, and pi over 2. And we might even go, yeah, let's go full. We'll go 2 pi over 3, and 3 pi over 4, and 5 pi over 6. Okay, so remember, tangent is sine over cosine. So you could say it's going to be sine x over cosine x if you want. So I know that sine of 0 is 0, cosine of 0 is 1, so tangent of 0 is 0. For pi over 6, sine of pi over 6 is 1/2, cosine of pi over 6 is the square root of 3 over 2. The 2's cancel, that becomes 1 over root 3, which we often rationalize as the square root of 3 over 3. Right? I'm just multiplying this by root 3 over root 3. For pi over 4, sine of pi over 4 is the square root of 2 over 2. Cosine of pi over 4 is the square root of 2 over 2. Oh, look, I divided something by the same something. Anything divided by itself is 1. For pi over 3, sine and cosine switch values from pi over 6. So sine of pi over 6 is 1/2. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. The 2's cancel, and root 3 over 1 is just square root of 3. And finally, tangent of pi over 2 is undefined. Right? It's sine is 1, cosine is 0, and 1 divided by 0 is undefined. And then for 2 pi, so the angles in the second quadrant, 2 pi over 3, 3 pi over 4, and what's the very last column? Oh, it's sine of x over cosine of x. Yeah. I'm just using that to help me figure out what the y values actually are. Right, because tangent of x is equal to sine of x over cosine of x. So then in quadrant 2, tangent is negative. But the values are the same for the same reference angles. So pi over 3 and 2 pi over 3 both have pi over 3 as the reference angle. Tangent of pi over 3 was the square root of 3. Tangent of 2 pi over 3 is going to be the negative square root of 3. Tangent of pi over 4 was 1. Tangent of 3 pi over 4 is going to be negative 1. Tangent of pi over 6 was the square root of 3 over 3. Tangent of 5 pi over 6 has the same reference angle, so it's going to have the same value, except it's going to be negative since it's in quadrant 2. And I ran out of room, but tangent of pi would also be 0. So let's take a look about graphing this. Do I have enough room? Yeah, enough room. So when I start graphing tangent, I usually start by graphing where tangent's 0. So here's 0. And over here at pi, it's also equal to 0. And also you could go pi in the other direction, right? If you went negative pi, right? So in my unit circle, if I go pi, that's halfway around the circle, and I get to this other point here where tangent is 0. But if I go negative pi, I get to the same point, right? Halfway around either way, is going to be getting me to the same point. Okay, so, and then the pi over 2, where it's undefined, I'm going to get a vertical asymptote. And typically, graphically, when you're graphing something, graphically, when you have division by 0, I should say a non-zero number divided by 0, that typically means we have a vertical asymptote. We could start talking about the idea of a limit, and maybe I'll mention it kind of a little bit here. So then let's see what's happening graphically. So pi over 2, maybe that's like 1, that's like -1. So at pi over 4, which is halfway between 0 and pi over 2, I'm going to get a value of 1. And I'm not really going to plot these points. I could. Square root of 3 is about 1.75. That's like, I don't know. At pi over 3, it's kind of like, but like it's not super necessary. And at pi over 6, square root of 3 divided by 3 is like 0.6-ish. Okay. But the shape that you're looking for is kind of like that. So here's a couple things to think about when you're graphing this. At least a couple things that I think about. When you're looking at sine over cosine, and you're in, say, the first quadrant. So you're in the first quadrant of the unit circle. This point is 1, 0. This point is 0, 1. And your angle theta is moving closer and closer and closer to being pi over 2 radians. So when you get really, really, really close to the angle being pi over 2, but still in the first quadrant, so less than pi over 2, right? So we're like right here. Sine over cosine, well, the top is getting closer and closer and closer to 1, and the denominator is getting closer and closer and closer to 0. So like you can get really, really close to 1 over 0. You can get something like, 0.99999 over 0.000001, right? Maybe you have something like that. Well, if you have something like that, that's going to be a really big number, because you have a number that's almost 1 divided by like 1 over a million. And 1 divided by 1 millionth is a million. So the idea here is that when you get really, really close to having something divided by 0, your fraction gets very, very large. And so we have a vertical asymptote where the values go up to infinity. Or they increase without bounds, as they technically more correctly saying it. Go
I have
ahead.
a question. So can we say that we have like a vertical asymptote wherever we have an undefined like function?
I would say we have a vertical asymptote where we have division by 0.
Okay, thank you.
And the reason I clarify that is because there are other ways a function can be undefined, like taking a square root of a negative. Right? The function y equal to the square root of x is certainly undefined when x is negative, but we don't have vertical asymptotes there.
Okay, thank you.
So yeah, it has to be undefined in this specific way. So you get a vertical asymptote where you have division by 0, or wherever you have a log of 0, right? Because logarithmic functions also have vertical asymptotes. Okay, so yes, to your question, we're going to have vertical asymptotes where we have division by 0, which means we're also going to have a vertical asymptote at negative pi over 2. Because at negative pi over 2, right, you would be down here, and basically tangent is undefined at the top and the bottom of the unit circle. At pi over 2, at 3 pi over 2, at 5 pi over 2, at 7 pi over 2, and that, right, you just keep going around and around and around and around and around. Every odd multiple of pi over 2, you're going to have a vertical asymptote. But on the left side here, well, I suppose I could say, right, we kept going further past pi over 2. So over here between pi over 2 and pi, we're getting these values. So we're getting, right, negative root 3 and negative 1 and negative root 3 over 3. So we're doing this kind of deal. Like that. Now, this is not the period of tangent that I usually want to graph. But I should stress, this is one full period of tangent. Tangent, unlike sine and cosine, has a period of 1 pi, whereas sine and cosine have a period of 2 pi, unless you've changed it, right? If you have just tangent of x, or just sine of x, or just cosine of x, their periods are for tangent of x 1 pi, for sine of x and cosine of x 2 pi. So this is one full period, meaning once you've got this, it's just going to repeat. So I'm going to take this part and move it over here. Here's my next vertical asymptote at 3 pi over 2, and it's going to look like this. And then it's going to look like this. So it's kind of interesting that the values of cosine repeat, or sorry, the values of tangent repeat after just pi. So typically when I draw tangent, I don't do all this, although you could. Here's the way you should draw tangent if you're just trying to draw. If I was going to draw just tangents, here's what I would really draw. Say, hey, look, I know I've got vertical asymptotes at pi over 2 and negative pi over 2. Really, every odd multiple of pi over 2. And then I know it has this shape. And usually I like to throw in the values for pi over 4 and negative pi over 4. I know tangent of pi over 4 is 1. And the way I space this out is I know that pi over 4 is approximately 3/4. So this length should be a little shorter than that length there because 1 is bigger than 3/4. So here's pi over 4. And here's negative pi over 4. Tangent of negative pi over 4 is going to be -1. So I plot this one. And here's kind of the way I graph this. When you're graphing the part that goes through the origin, it should kind of look like the line y equals x, at least right around there. And then we're going to kind of go up like that, and we're going to go down like that. And then it repeats. If you only have to draw one period, this is the period you should draw, from vertical asymptote to vertical asymptote.
James, I have a quick question.
Yeah.
Can you explain why we have a vertical asymptote at negative pi over 2?
Sure. So if you look at your unit circle, this angle up here is pi over 2. This angle over here is pi. This is 3 pi over 2. This is 2 pi. And we know the points are 1, 0, 0, 1, -1, 0, 0, -1. And we know the tangent of our angle is sine of our angle over cosine of our angle, which is the y coordinate over the x coordinate. Okay, so clearly tangent of pi over 2 is 1 over 0, which is undefined. Same thing for tangent of 3 pi over 2. Right? Whenever the cosine part of the angle is 0, tangent's going to be undefined, and we're going to get a vertical asymptote. Well, for negative pi over 2 is just pi over 2, but in the clockwise direction. So when your angle is negative, instead of going this way, right, that would be pi over 2. Negative pi over 2, we're going that way. But negative pi over 2 still gets me to a place on the unit circle where the cosine value is 0 and the sine value is not, meaning that we're still going to get division by 0. So tangent of negative pi over 2 is, well, it's -1 over 0, which is undefined. Does that clarify things?
Yeah, that helps a lot. Thank you.
Good. Welcome. So if you're asked to graph tangent, this is what you should graph. Really, so I should say, if you're asked to graph one period of tangent, you really just want to graph this period right there, the middle period between negative pi over 2 and pi over 2. It is also technically correct to graph, say, like this single period. But if you have to graph one period of a thing, it's usually better, preferred to graph a period where you don't have a giant vertical asymptote in the middle of it, where the graph you're graphing is not broken up. So yes, if you graph this and someone else to graph one period of tangent, technically you would be correct. No one will. Do you know what I mean, right? Like this is not the right choice to make if you're asking to graph one period of tangent. Okay, so let's talk a little bit more about graphing tangents. So we could change, so we don't talk about amplitude for any functions but sine or cosine. We can still have a phase shift where you shift it horizontally, a vertical shift, or horizontal stretch, meaning we can change the period. And typically changing the period is the thing we really do for tangent. So if I want to graph, say, y equal to tangent of, say, 1/3 x. Well, the same rules apply as for sine and cosine. That is graphing y equal to sine of 1/3 x. I know that the period would be 2 pi divided by 1/3. Divided by 1/3 is like multiplying by 3. So that's 2 pi times 3, which is 6 pi. The only difference is that for tangent and cotangent, the original period isn't 2 pi. The original period, right, so the period of regular tangent of just x is pi. So the period of anything else, instead of being 2 pi divided by the coefficient of x, it's going to be pi divided by the coefficient of x, which is going to end up being 3 pi. So the rules are still the same in that you take your original period for the function, 2 pi for sine and cosine, and secant and cosecant, 1 pi for tangent and cotangent, and you divide that by whatever is multiplying x. So to graph this, my period is going to be 3 pi. And usually the way I think about graphing tangent is, okay, whatever the period is, half of that to the right of the origin and half of that to the left of the origin, that's going to be where your vertical asymptotes are. So my vertical asymptote is going to be over here at 3 pi over 2. And my vertical asymptote is going to be over here at negative 3 pi over 2. Right? I have a horizontal stretch. Normally, my vertical asymptote would be like here and here. So my function, so again, right, just like with my, erase the wrong one. With my regular tangent function, period's half, your vertical asymptote's half of the period, and then halfway between those, you get the place where it's equal to 1. Well, it's going to be true here too. And halfway between 0 and 3 pi over 2, so at 3 pi over 4, which is like about 2. It's a little more than 2, but it's fine. The y value is going to be 1. Because if you plug in 3 pi over 4, look at what happens. Tangent of 1/3 times 3 pi over 4, the 3's cancel, and you get tangent of pi over 4, which is 1. Right? I'm just stretching out where my y values occur, right? Before, my y value of 1 it was at pi over 4. Now I've stretched it out horizontally by a factor of 3. So the same y value of 1 is now occurring 3 times as far away for the x coordinate. And then the same kind of thing is true for, right, for the other side. At negative 3 pi over 4, I'm going to get a value of negative 1. So here's my tangent graph now. Or one period of my tangent graph. It's just been stretched out horizontally. And to be perfectly honest, that's most of what we do with tangents. But you can do other shifts and transformations, but most of the time we're just stretching tangent horizontally or compressing it horizontally. Okay, so very briefly, I'm going to talk about the other 3 trig functions. Really, you just kind of need to see their original form because we're not going to do much else with them. We're not really going to do anything else with them, which you will probably see in the future classes. Let's talk about cotangent. So here's the nice thing about trig functions. If you know what a function looks like, you know what its cofunction looks like. So we know what sine looks like. Cosine looks a lot like sine. In fact, it's literally just the sine function shifted. Cotangent is going to look a lot like tangent. It's going to be the tangent function shifted and also flipped. Secant and cosecant will also look very much the same. So let's graph cotangent. Which I'll remind you is cosine of x divided by sine of x. All right, so here's the thing. This function, instead of being undefined when cosine is 0, it's going to be undefined when sine is 0. So this function is going to be undefined when we're at this point here, where sine is 0, at an angle of 0, or this point here, when sine is 0, and the angle is pi. So if I start graphing this, let's say pi is there, let's say 2 pi is there, let's say negative pi is there. So right, so if I start here at 0, undefined. So vertical asymptote at 0. I'm not going to draw it because I just don't want to draw the y-axis again. And then if I go over to pi, it's also going to be undefined there because you're going to get negative 1 over 0. So you're going to have vertical asymptote at pi. I go all the way around to 2 pi, undefined again. So right, just like with tangent, the period of cotangent is pi, meaning every length of pi, you're going to get the same feature. So if you're talking about where the vertical asymptotes are, they're all going to be pi apart, even to the left. But if you go negative pi, you're just going clockwise. So if you start here and go negative pi, oh look, you're still going to end up right there where it's undefined. And then in between, I should say exactly halfway between every vertical asymptote pair, you're going to get an intercept. So you're going to get an intercept at pi over 2. You're going to get an intercept at 3 pi over 2. You're going to get an intercept at negative pi over 2. Right? So for cotangent, on the sides you get vertical asymptotes, and at the tops and bottoms you get intercepts, right? Because here you get 0, 1, and cotangent is going to be 0 over 1, which is 0. Or down here, the point 0, negative 1, cotangent of 3 pi over 2 is going to be 0 over negative 1. Same deal over here. Right, negative pi over 2 is just getting you back to that point right there. Okay, so the only difference is tangent goes up from left to right, but cotangent goes down from left to right. And here's the way I kind of think about it. 0 to pi over 2. 0 to pi over 2. Quadrant 1, everything's positive. So from here to here, it has to be positive. But it can't do this because I don't have a vertical asymptote there. So what has to happen is, right, in fact, actually, I have a vertical asymptote right here, so I have to kind of do this. And then from pi over 2 to pi, cotangent's negative. So I have to do this. And I know what it looks like because I know it looks a lot like tangent. Sorry, you shouldn't actually be on the vertical asymptote, it's just something you accidentally. And then there's one full period. We could stop there, or you could draw more, right? But the rest is just going to look the same. Cotangent literally looks like you took tangent, shifted it pi over 2 to the right or left, same difference, and then flipped it over, did a vertical reflection, or did a horizontal reflection, right? It's kind of the same either way. So yeah, cotangent and tangent, very similar to each other. They look a little bit different. Questions about this one before we talk about secant and cosecant? I will mention, I'm not going to test you on the graphs of cotangent or secant or cosecant. I might have something about the graph of tangent on your final, but this graph and the next 2 graphs, I am not going to test you on, but I do want you to have seen them because they will come up in the future. It is worth noting the cotangent is undefined at negative pi, at 0, at pi, at 2 pi, at every multiple of pi. Whereas tangent, I erased tangent. Tangent is undefined at every odd multiple of pi over 2, right? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, forever, ever, ever. Negative pi over 2, negative 3 pi over 2. They're undefined at opposite corners of the unit circle. So, right, here are the places where cotangent is undefined. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, right? Even multiples of pi, odd multiples of pi. Here's where tangent is undefined. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, odd multiples of pi over 2. Okay. Secant and cosecant, I think, are actually way easier to graph than tangent and cotangent. So let's talk about cosecant. Cosecant, which is 1 over sine. And here's actually a really important idea just in general. If things are reciprocals of each other or inversely related, although I will hesitate to say inverse, they're not inverse functions, right? Because an inverse function is something different than a reciprocal function. But so these are reciprocals of each other. Then if sine gets small, cosecant gets large. And if sine gets large, cosecant gets small. So here's what I'm going to do. I want more to the left here. I'm not going to plot points, although we could. I'm going to graph sine. So there's 2 pi, pi, pi over 2, 3 pi over 2, and then so that's 1, that's negative 1. And let's go also negative pi over 2 and negative pi. So fully graph as much as sine. So let's graph sine. I'm going to graph sine in red and dashed. So sine of 0 is 0, and sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. Sine of 2 pi is 0. Right? A full period of sine looks like this. Can you guys hear my wife? I can hear her, which is fine. She's talking on her phone. Okay, so there's the sine function. Okay, now here's the deal. Cosecant is 1 over sine. So at pi over 2, sine of pi over 2 is equal to 1. So in fact, right, sine of pi over 2 is equal to 1. So cosecant of pi over 2 is 1 over sine of pi over 2, which is 1 over 1, which is 1. So whatever sine value is, cosecant is a reciprocal of that. In this case, they're the same, because the reciprocal of 1 is 1. But now here's the idea. As the sine values get smaller, right? Sine values get smaller, the cosecant values get larger, right? Specifically, here's another one that's nice. I know that, and you know that, sine of pi over 6 is 1/2, which means cosecant of pi over 6 is the reciprocal of that, which is going to be 2. So over here at pi over 6, which is maybe like about here-ish, right? My sine value is 1/2. My cosecant value is 2. So here's the way I think about this. As the sine value gets smaller and smaller and smaller and smaller and smaller and smaller, the cosecant reciprocal value gets larger and larger and larger. Same deal over here. As the sine values get smaller and smaller and smaller, the cosecant values get larger and larger and larger. And wherever sine is equal to 0, cosecant is going to be 1 over 0, which is undefined, which means we're going to have a vertical asymptote. Same deal over here, except now the values are negative. Right? If sine of 3 pi over 2 is equal to -1, so is cosecant, because the reciprocal of -1 is -1. And then as the sine values get closer to 0, the cosecant values get further away from 0. Same deal this way. So there's one full period of the cosecant function from 0 to 2 pi. Sine does this, cosecant does this. And then if you really want, you can erase the guiding sine graph that you drew. And there's cosecant. And you can draw more of it if you want right here. These are not parabolas. People have said they kind of look like parabolas. They do kind of look like parabolas, but parabolas don't have vertical asymptotes, and these definitely do have vertical asymptotes. So not exactly parabolas, but do kind of look like they are parabolic. So that is how I would encourage all of you when you have to graph cosecant sometime. Say, oh, I know how to graph sine, and then instead of the graph getting closer to the x-axis, it's going to go away from the x-axis. Either away above if you're already above, or away below if you're already below. Also, this kind of re-emphasizes the fact that if your function is already positive, its reciprocal is also positive. If your function is already negative, its reciprocal is also negative. It looks like I'm not going to get to most of the next half of this, which is talking about solving trig functions, but I will definitely do at least one example after I graph secant here. So here's the nice thing. Graphing secant is exactly the same process as graphing cosecant. So if I want to graph secant, I remember it's the reciprocal of cosine. Okay. So cosine also has a period of 2 pi, goes in half and half and half. And then maybe also do 1 or 2 of those to the left. Cosine starts high at 1, and then goes middle, and then low, and then middle, and then high. So then secant, reciprocals. And so when I'm doing secant or cosecant, I'm always going to say, all right, I know that when the cosine function or the sine function is 0, you're going to get a vertical asymptote. And then cosine is equal to 1, secant is also equal to 1. Cosine gets closer to 0, secant moves away from 0. Cosine gets closer to 0, secant moves away from 0. If cosine is -1, secant is also -1. Cosine gets closer to 0, secant moves away from 0. Cosine gets closer to 0, secant moves away from 0. There's one full period of secant. So that's how I would really, really, really encourage you all to graph secant and cosecant. It's kind of the easiest way to do it, I think. Okay. So yeah, it's a little more time than we usually spend talking about that, but I do think it will be worth your while to have seen that when you have to do those things in your next Calc 1 class. Because whatever Calc 1 class you take, they will definitely talk about secant and cosecant. Hopefully they will draw the graphs for you and you can kind of talk about them, but they might not. They might just talk about their derivatives. So now you've seen them, at least you have an idea what they look like. Solving trig equation. Z. So let's see what we've got. So typically, most of the time if someone's asking you to solve a trigonometric equation, they're usually going to limit the number of solutions to being within one full revolution of the circle. So find all solutions in the domain where x is between, that's not how I want to write that, where x is greater than or equal to 0 and less than 2 pi. It's typically written as a greater than or equal to 0 and a less than 2 pi because we kind of have all decided together that it doesn't make sense to say that 0 and 2 pi are both answers because they're kind of on the same spot of the unit circle. So it's kind of like duplicating an answer. It's not super terrible. It's just something that's typical. So I want to solve sine of x equal to the square root of 3 over 2. Most of these questions, by the way, are going to be values that we recognize from our special angles. So our job here is to find all, which there usually more than one, solutions of this equation. So first thing I want to look for is, what's the reference angle? What's the angle in quadrant 1 where sine is equal to the square root of 3 over 2? Is it pi over 6 or is it pi over 3? Or is it pi over 4?
Pi over 3.
Right, it's pi over 3. So we know the reference angle is pi over 3. The other job we have to do is to ask ourselves, what quadrant? What quadrants is sine positive? Right, because we want sine to be positive square root of 3 over 2. So quadrants which?
Would it be 2 and 1?
Yes, exactly. Right, we know that sine is positive in the first and the second quadrant. So here's what our final job is. We have to say, okay, we need the angles in quadrants 1 and 2, whose reference angle is pi over 3. Well, in quadrant 1, the reference angle is just the angle. So our angles are going to be pi over 3 in quadrant 1. And what's the angle in quadrant 2, whose reference angle is also pi over 3? Well, I know it's something pi over 3. How much pi over 3? 2 pi over 3? 3 pi over 3? 4 pi over 3? 5 pi over 3? It's 2 pi over 3. So right in quadrant 1, pi over 3 has the reference angle pi over 3. In quadrant 2, the reference angle is pi over 3, and the actual angle is 2 pi over 3. Let's answer the same question, except let's now ask, what if I wanted to solve the equation sine of x equal to negative root 3 over 2? Okay, well, the reference angle is still the same. Because again, so when I'm finding the reference angle, I'm totally ignoring the negative sign. I'm just asking myself, okay, where is sine equal to positive root 3 over 2 in the first quadrant? Oh, it's pi over 3. And now, instead of quadrants 1 and 2, we want answers in quadrants 3 and 4. So, in quadrant 3, right, there's my angle, whose reference angle is pi over 3. The actual angle is pi plus pi over 3, which is going to be 4 pi over 3. And in quadrant 4, well, the angle whose reference angle is pi over 3 in quadrant 4, it's all the way 1/4 evolution minus pi over 3. That's going to be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3, which is 5 pi over 3. So that's kind of the gist, is that we're going to be looking for the right reference angle in quadrant 1, and then we're going to ask, okay, what's the actual angle in the necessary quadrants that have that same reference angle? Let's look at another example. Let's say I want to solve, I'll do this one first. I want to solve secant of x is equal to the positive square root of 2. I never like dealing with secant. Instead, what I would really ask myself is, where is the reciprocal cosine of x equal to the reciprocal 1 over the square root of 2? Or if you prefer to rationalize, root 2 over 2. Okay, what's the reference angle? Pi over what?
Wait, for which one?
For pi over 4. Oh, pi over 4. For root 2 over 2. The reference angle is pi over 4. Right? Because we know cosine of pi over 4 is root 2 over 2. So then we know the reference angle, and then we have to ask ourselves, where is secant or cosine, either way, where is it positive? Well, that's going to be in quadrant 1 and quadrant 4. So I need a reference angle of pi over 4. Well, in quadrant 1, your answer is just the reference angle. So our answers are going to be pi over 4. And the angle in quadrant 4, whose reference angle is pi over 4. Well, that's going to be a full 2 pi minus pi over 4. Which is 8 pi over 4 minus pi over 4, which is 7 pi over 4.